Hello everyone, I am Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today I am going to discuss about the internal field in solids, and we are also going to derive the Clausius-Mossotti equation. So in our previous lectures we have already covered the topics Introduction to Dielectrics and the types of polarization. So we are going to discuss about this internal field and Clausius-Mossotti equation. So let us see the brief outline of how we are going to discuss about this topic. First, we'll try to understand what a polar dielectric is, and then we will derive the expression for the internal field in solids, and then we will obtain the derivation for the total internal field. Combining all the internal fields, we will get the total internal field, and then we will derive this equation, Clausius-Mossotti equation. So first we will see what a polar dielectric is and what happens when it is placed in an electric field. So polar dielectrics are materials that have permanent dipole moments. So whenever you take a polar dielectric material, they are polarized. So they have permanent dipole moments but with random orientations. These dipole moments are in random orientation. Now if you see this figure here, the first one, each one is a dipole, negative and positive, separated by a small distance, but they are separated. So they are having permanent dipole moment. This is in the absence of electric field. No electric field means E is equal to 0. So when E is equal to 0, these are having permanent dipole moments, but their orientations, if you see, they are in random direction. Random means in any direction they like. So here minus plus, here minus is pointing downward and here it is pointing upward. Like that, the orientations are different. But whenever we place this polar dielectric in an electric field, the partial alignment of dipoles takes place. These dipoles, which are randomly oriented, will now start aligning towards the applied electric field. So whenever we are applying an electric field like this denotes the applied electric field. So what happened to these dipoles? You see, they are getting oriented partially. So all the minuses are pointing towards the positive plate if you are applying the electric field like this, and all the positives are pointing towards the negative side. So in the presence of an electric field, they show partial alignment of dipoles, and in this case the net dipole moment will not be equal to 0. So they possess some dipole moment inside due to the presence of permanent atomic dipoles. So what we need to understand about a polar dielectric is they possess some dipole moment due to the presence of permanent dipoles, and these are randomly oriented when no field is applied, and they align themselves when an electric field is applied, and the dipole moment and polarization will increase when an electric field is applied. Why it increases? Because the dipoles start aligning in the direction which gives some extra polarization. This extra polarization is due to the alignment of the dipoles in the direction of the applied field. So what about the resultant polarization now? P is equal to the polarization that is already existing due to permanent dipoles, because we have seen that whenever we are talking about polar dielectrics, they already possess some permanent dipole moment. So this is the already existing dipole moment due to the permanent dipoles, and then the polarization which is induced due to the electric field. So whenever we are placing them in an electric field, they are partially aligned, and because of that there is some polarization. So this is the equation we have. The total polarization P is the polarization due to the permanent dipoles and the polarization due to the applied electric field or induced. So now we are going to see what a local field or an internal field is. We may represent it by EI or E local. Because it is localized, we may also call it as E local. So what is the definition of this local field? In dielectric solids, the atoms or molecules experience not only the external applied electric field, but also the electric field that is produced due to the dipoles. So when we have seen about these dielectric materials, especially the polar dielectrics, they already possess some electric dipoles. So the electric field that is produced due to these dipoles is also getting added up. So the resultant electric field acting on the atoms or molecules of the dielectric substance is called the local field or internal field. So this is what we call as local field. A resultant internal electric field acting on the atoms or molecules, we call it as local field or internal field. Now let us try to understand this with the help of this diagram. So we consider a dielectric material which is placed in an external field. So we take a dielectric material and we are placing it in an external field E1. So now we have considered this is the dielectric material. This is a dielectric. This we are placing in an electric field. This is positive, negative. So this is how the electric field is. So when I am connected this plate to positive, this plate to negative, means this is positive. It is very important to understand this charges, how they are getting oriented. So now, how will be the field? Applied external field will be always from positive to negative. So this I am calling as E1. What is E1 here? E1 is the applied external electric field. So this is positive, negative. So E1 is pointing this side. Now, when I have placed this dielectric in this electric field, what happens? Opposite charges get induced on the surface of the dielectric. Because this is positive, the negatives will get attracted. So negative charge is induced. And on the other side, positive charge is induced. Positive is induced on the other side. Now, because of this, there will be an electric field pointing from positive to negative. So this is E2. So what is E2 due to? It is due to the opposite charges that are induced on the surface of the dielectric. So as a result, what is happening? Opposite type of charges are induced on the surface of the dielectric. So E1 due to the applied field, E2 due to the induced charges on the surface of the dielectric. So the resultant will be E is equal to E1 minus E2 due to these two. So whenever we have to consider, we will consider E1 plus E2, and because the direction of E2 is in the opposite, the resultant will be E1 minus E2. This figure we have already discussed, polar dielectric in an electric field. So we have placed a dielectric material in an electric field and we have seen the fields. E1 is the applied field, E2 is the induced field, E is the resultant. Now what we are seeing here is, you will imagine a cavity, a spherical cavity inside the dielectric, which consists of number of dipoles. So here, if I see the cross section of the sphere, it is like this. So how it is like this? On the surface here, the dielectric we are getting negative induced. So because the negative is induced here and there is positive on this side, the spherical cavity, if I take, on this side of the spherical cavity positive charges will be induced and on the other side the negative charges will be induced. So inside the sphere, what are there now? Dipoles are present. And we are considering a dipole at the center of the spherical cavity. And the dipole is experiencing the following fields now. What are the fields that this dipole, which is placed at the center, experience due to the externally applied field E1? So the total internal field experienced by the dipole will be given by E local or EI. So what is E local or EI representing? It is the total internal field that is experienced by the dipole. So that is equal to E1 plus E2 plus E3 plus E4. So let us see what are these E1, E2, E3 and E4 are. So E1 is due to the applied external field. So this is E1 applied field because we have connected it like this, positive, negative. So E1. Next, what is E2? E1 is due to the applied external electric field and E2 is due to the induced charges on the dielectric. So these are the charges that are induced on the surface of the dielectric. And this gives rise to an electric field E2 and pointed from positive to negative. So this is E2. Then we have field E3 arising from dipoles inside the sphere. So inside the sphere there are many dipoles and depending on the crystal symmetry for isotropic materials, E3 is equal to 0. Because of their symmetric nature, E3 inside the sphere, E3 becomes 0. Then E4 is due to the polarization of charges on the surface of the spherical cavity. This is the major contribution now. So now on the sphere, what is happening? Because of the negative charge induced on the surface of the dielectric, there will be positive on the surface of the sphere here and on the other side it will be negative. Now E4 is due to these induced charges on the surface of the sphere and this is called as the Lorentz cavity field. Now let us find out what is E4 equal to. The surface charge density on the surface of the spherical cavity is P cos theta. So in the figure we have seen the surface charge density is given by P cos theta. And if ds is the area of the surface element we have taken, we have considered a small surface element ds. So then the charge on the small element Q1 will be the normal component of the polarization multiplied by the area of the surface element. So what do we get? Q1 will be equal to P cos theta, that is the surface charge density, multiplied by ds, the small element under consideration. Now what we are going to do is we'll keep a test charge Q at the center of the cavity. So from Coulomb's law, the force experienced between the surface charges, we have already discussed Coulomb's law. So what is Coulomb's law? Whenever you have two charges here, Q and Q, one is plus Q and minus Q, separated by a distance R. So what Coulomb's force law says is F is directly proportional to the product of the charges. I'll write this as Q1, Q2, and inversely proportional to the square of the distance, or we can remove the proportionality sign and write it as 1 by 4 pi epsilon naught Q1 Q2 by R square. Now, when these two charges are opposite or unlike, then there will be force of attraction, and when they are same, it will be repulsion. Now what will be the force dF due to the small element we are considering? Now the general formula is 1 by 4 pi epsilon naught Q1 Q2 by R square. But what we want the Coulomb force for the area under consideration. So dF will be equal to 1 by 4 pi epsilon naught into P cos theta ds. This is the charge we have considered, multiplied by Q. So here our Q1 is what? P cos theta into ds, and Q2 is equal to Q. That is what we said. Let a test charge. Why we are placing a test charge? Whenever you have a charge there, you place a test charge. What is the force of attraction or repulsion, you can check. If it is repelling, means they are similar charges. If they are attracting, means they are opposite charges. So now from this, I can write dF by Q. dF is here Q. I can take Q onto the other side. So we get dF by Q will be equal to 1 by 4 pi epsilon naught P cos theta ds by R square. This is equation 3. Now once you know dF by Q, you can get the field easily because E is equal to F by Q. So this gives the resultant electric field E4. So E4 is equal to dF by Q, that is equal to 1 by 4 pi epsilon naught P cos theta ds by R square. So we are writing E4 as equation 4. This is equation 4, we are getting E4. So now this electric field, it can be resolved into two components. Like what we do, it is not along the x-axis or the y-axis, it's at a certain angle we have taken as theta. So one component is always along the direction of P and the other one is perpendicular to it. So we have one component along the direction of P and the other one perpendicular to it. So the perpendicular components cancel themselves, leaving the horizontal components. So perpendicular components, what they have happening, they are cancelling. So if one is in the upward direction and the other is in the downward direction, this is the direction of P, they get cancelled. But what we are left with is only the horizontal components. So the sum of such horizontal components, we are taking the sum of all the horizontal components, leaving the perpendicular because they are cancelling out. What we get is E4 is integral dE4 cos theta. So you have to integrate over the whole area. So let us substitute for dE4. So what we have for dE4, 1 by 4 pi epsilon naught P cos theta by R square, and now you have cos theta into ds. And what is ds here? It is the surface area of the ring. Because whenever for a spherical cavity you take one small element and cut it out, it will be in the form of a ring. And what is the surface area of a ring given by 2 pi r square sine theta into d theta. So we are going to substitute for ds the surface area, small surface area due to that element we have considered. So 2 pi r square sine theta d theta. So 1 by 4 pi epsilon naught P cos square theta into 2 pi r square sine theta d theta. This is what we have substituted for ds upon r square. Now the limits are going to be 0 to pi. What are the limits? From 0 to pi. Now whatever is common inside, I can take it outside. So P, we can take it outside. 1 pi and 1 pi will get cancelled. 2 will go 2 times. So what is left outside here is P by 2 epsilon naught integral 0 to pi cos square theta sine theta d theta. R square also is getting cancelled. So what is left? Cos square theta sine theta d theta in the integral. P we are taking it outside because it's constant. So P by 2 epsilon naught integral 0 to pi cos square theta sine theta d theta. Now I'll have to solve the integral and get the value. So for that what I do, I'll consider let cos theta be equal to z. Just to solve this integral, we have considered cos theta is equal to z. Now when cos theta is equal to z, what will be the derivative of cos theta? Minus sine theta d theta will be equal to dz. and the limits also will vary from 1 to minus 1. So 0 to pi, if you substitute, you will get the limits from 1 to minus 1. So how we are going to write it now? E4 will be equal to P by 2 epsilon naught integral 1 to minus 1 z square minus dz. Cos square we have, so that we are writing as z square, and for minus sin theta d theta we are writing minus dz. So I can take out this minus outside, so minus P by 2 epsilon naught integral plus 1 to 1 z square dz. So we'll have to simplify this. What will be the integral? So plus 1 to 1 z square dz. So we know what is integral of z square. It will be z cube by 3. Z power n plus 1 by n plus 1. What are the limits? From the lower limit plus 1 and upper limit minus 1. So we will find out this value and bring it and substitute here. So what is z cube by 3? First I will substitute the upper limit. So minus 1 whole cube by 3 minus lower limit is 1. So 1 whole cube by 3. So minus 1 whole cube is minus 1 by 3 minus again 1 cube is 1 by 3. So minus 1 by 3 minus 1 by 3 will give us minus 2 by 3. So I am going to substitute here. So E4 is now equal to what? Minus P by 2 epsilon naught into minus 2 by 3. 2 will get cancelled. We have minus into minus plus. So P by 3 epsilon naught. So what we are getting? E4 is equal to P by 3 epsilon naught. This is equation 8. So just doing the simple integration, we are getting E4 to be equal to P by 3 epsilon naught. Now we are going to substitute the value of E4 in equation 1. What was our equation 1? EI or E local is equal to E1 plus E2 plus E3 plus E4. So this was our equation 1. So in this, what we have seen, E3 is becoming 0 inside whatever dipoles are there. Electric field due to that is simply 0 because of the symmetry. Then what is left out when E3 is equal to 0? We have EI is equal to E1 plus E2 plus E4. And what we have seen is E1 and E2 are opposite in direction and the resultant is given by E. Now, if E1 is in this direction, E2 is in the opposite direction. So, the resultant E will be equal to E1 minus E2 or E1 plus of minus E2. So, we are getting E. If you are considering the direction also, then E1 minus E2. So, what will be the total resultant field now? EI will be equal to E plus E4. E is the resultant of E1 and E2. And E4 is what we have derived now. This is due to the charge that is induced on the surface of the sphere and that comes out to be P by 3 epsilon naught. So, the internal field EI or the local, E local is given by E plus P by 3 epsilon naught. Now, we are going to derive the Clausius-Mosotti relation. This is a very important relation and very useful relation in obtaining the polarization. So, the relation between microscopic and macroscopic. So, when I say microscopic here, it means which are small in size of the order of 10 power minus 6. Macroscopic means which we can measure. So, we are going to get a relationship between these quantities using the Clausius-Mosotti relation. So, first we will start with the polarization vector. What is this polarization vector? P is given by n mu. What is n here? It is the number of molecules per unit volume and mu represents the average dipole moment. So, P is equal to n into mu. And we also have seen mu is equal to alpha E. Here it is due to the internal, whatever field we have local, we have found out that is alpha EI. So, EI here is the local or the internal field. Okay, and we also have found EI to be equal to E plus P by 3 epsilon naught. Now we are going to substitute 2 and 3 in 1. What is our equation 1? P is equal to N into mu. So here mu is equal to alpha EI and EI is equal to E plus P by 3 epsilon naught. So these two equations we are going to substitute now. So P is equal to N mu and mu is equal to alpha EI and EI is equal to E plus P by 3 epsilon naught. So this is how we are going to substitute in this equation. So P is equal to N into alpha EI. So we have N alpha and what is EI equal to? E plus P by 3 epsilon naught. We have substituted here. So it is just the substitution of equations 2 and 3. That is the formula for mu and the value of EI we have taken and we have substituted. Now it is all simply substitution and taking transpose onto the other side to get the required value. So what I am going to do is N alpha into E is N alpha E plus N alpha into P by 3 epsilon naught will be N alpha E plus N alpha P by 3 epsilon naught. I am just going to do it here. What we are getting by multiplying. No? So N alpha E plus N alpha into P by 3 epsilon naught. Now I'll be taking this N alpha P onto this side. So P minus N alpha P by 3 epsilon naught will be equal to N alpha E. Here P is common in both the terms. So I can take out that as common. 1 minus N alpha by 3 epsilon naught is equal to N alpha E. So what will P be equal to now? N alpha E, the whole thing goes to the denominator. 1 minus N alpha by 3 epsilon naught. This is the value of P we got. We will call this as equation 4. N alpha E by 1 minus N alpha by 3 epsilon naught. We are getting it as equation 4. Now, we know the formula for polarization P is equal to epsilon naught E into epsilon R minus 1. This is the equation we have derived for the polarization. Now, let us substitute this for P. So, we are going to equate equations 4 and 5 because the left hand side is the same. So, the right hand side also has to be the same. So, N alpha E by 1 minus N alpha by 3 epsilon naught. This is what we got for P equal to in equation 4. And according to equation 5, P is equal to epsilon naught E into epsilon R minus 1. So, I am going to equate these two. N alpha E by 1 minus N alpha by 3 epsilon naught is equal to epsilon naught E into epsilon R minus 1. Now, we can write N alpha E. So, from here, how it goes, we'll see. N alpha, I can cancel E and E on both the sides and bring this epsilon naught into epsilon R minus 1 onto this side. So, we'll have 1 minus N alpha by 3 epsilon naught. So, this is what we get. I can bring this N alpha by 3 epsilon naught onto this side. So, N alpha by epsilon naught into epsilon R minus 1 plus N alpha by 3 epsilon naught. Because it is minus on this side, when it comes onto the other side, it becomes plus is equal to 1. So, what are the things we can take common now here? We can take N alpha by 3 epsilon naught, we can take common. This is 1. And here what we are doing, I have taken N alpha by 3 epsilon naught. So, I will be having 3 upon epsilon R minus 1 plus 1. Now, we will simplify. 1 is equal to n alpha by 3 epsilon naught. Taking the LCM, we have 3 plus epsilon r minus 1 by epsilon r minus 1. So this is 1 is equal to n alpha by 3 epsilon naught. Epsilon r plus 3 and minus 1 is how much? Plus 2 by epsilon r minus 1. This is epsilon r minus 1. So now we want epsilon r minus 1 by epsilon r plus 2. So I'll take it on to the other side. So epsilon r minus 1 by epsilon r plus 2 will be simply equal to n alpha by 3 epsilon naught. This is a very important result. Epsilon r minus 1 by epsilon r plus 2 is n alpha by 3 epsilon naught. Now what we are doing here is, if alpha m is a molar polarization and Na is the Avogadro number and rho is the density and m is the molecular weight, we know that capital N is equal to rho Na by m. So what we are going to do is, for capital N, we are going to substitute rho Na by m. So the relation we have is epsilon r minus 1 by epsilon r plus 2 is equal to n alpha by 3 epsilon naught. So in place of n, we are going to substitute this. So epsilon r minus 1 by epsilon r plus 2 will be equal to rho Na by m. In place of n, that is the number, we are going to substitute rho Na by m into alpha by 3 epsilon naught as it is. So we have put this alpha by 3 epsilon naught as it is. So this is the final expression for the Clausius-Mossotti relation. So this gives the relationship between the microscopic and the macroscopic quantities. So for any clarification regarding these derivations for the local field or the internal field and also the Clausius-Mossotti equation, you can refer to Concepts of Physics by H.C. Verma. Thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.